Now everyone, in this part of the video I'd like to prove the very first statement of the theorem. It says the following: if beta is smaller than r over m1, m1 is the maximum value of the absolute value of this two-variable function, which is the value of the derivative. If beta is small enough, then our function generated by Picard iteration is not escaping this box. Again, the rationale was that if this is already too big, around that point, this is where we start, then it might escape quickly. So we have to make this width of this box small enough so that the function does not escape this upper and lower bound, which is r units above and r units below from the central point y0. And this was the statement. This is Picard iteration. We start from y0, the constant function, and recursively define all the yns. And this particular choice, any choice that is less than r over m1, will guarantee that all the Picard iteration we generated here is not going to escape this box. That's what we're about to prove. So we will use a mathematical induction. First, we prove that statement for the very first case n equals 0, and explain that if we have a statement for n, we can deduce that is n plus first, the statement for n plus 1 is also true. So we start with n equals 0. The statement is that the constant function minus this constant y0 is going to be less than or equal to r, which is obviously true. This is 0. So this part is true. So let me explain again about the structure of the mathematical induction. It starts like this. For example, when n equals 0, we know y0 minus y0x minus y0 is less than or equal to r. And just using this fact and the only hypothesis we have, we can show that statement for y1 is true. y1 of x minus y0 still less than or equal to r. Once you have this y1 of x minus y0 is less than or equal to r, then we can use that statement to show that y2 of x minus y0 is less than or equal to r. So this is called mathematical induction. So repeating this one over and over, rather than repeating this over and over, we'll just make this general statement. If we have established the fact for some particular n, we can show the this index, the statement with the index n plus 1 is also true. That can be logically deduced from this condition and other conditions that was given in the statement. And of course, the way to relate yn plus 1 with yn is through the Picard iteration. So you can see this is exactly the Picard iteration rearranged with absolute value around it. And we've been using this technique a lot in our video. If you have the value of integral, and if you actually change the inside value to the positive and integrate, it's like the sum, and it necessarily gets bigger. So we have to estimate this part. And here's where we call the induction hypothesis kicks in. For the nth level, we know the function is trapped in this box. Therefore, t is trapped in a and x, and this yn value is trapped in between r, around y0. Therefore, this point is in that box that I showed earlier. Therefore, it is bounded by the maximum value. So here's you can replace this one with the maximum value m1 and make the quantity necessarily bigger, potentially bigger. So here's the statement. This whole thing is bounded by m1. So those things are shown here. This point is actually in between y0 minus r and y0 plus r. That gives you this upper bound. Therefore, this integral with constant m1 is easy to calculate. So I wrote them down here. And what we want to establish is that this thing is still less than r. m1 is there. Let's get rid of x minus a. What is the maximum possibility of x here? Is of course a plus beta. That's the right endpoint. So if I replace it with a plus beta, and it gets bigger, and you can see this is just a beta. So it's just beta times m1, and beta was small enough so that is bounded by r divided by m1. So if you replace that with a larger value, r divided by m1, you can see that's r. So what this proves is that if you assume yn is trapped in between two values, you can show that yn plus 1, any function value, must be trapped in between y0 plus r and y0 minus r as well. So you don't have to write down case for n equals 1 and 2 and 3 to make an assertion. This is an effective way of writing down those type of argument mathematically.